Good evening and welcome to Kopernik Observatory and AstroFest 2023. My name is Drew Deskur. I'm the director here at Kopernik. We've got an extraordinary list of programs, of speakers that will be happening both today and tomorrow. And we're really excited to have AstroFest 2023. This is our 41st AstroFest here at Kopernik, and we are many things up here, but we are number one, of course, is an observatory, and we're very fortunate to have a group of very dedicated amateur astronomers that are resident here at Kopernik, the Kopernik Astronomical Society, and their president, George Normandin, who is a very avid astrophotographer, is going to now come up and talk about George's best at Kopernik's, whatever he's going to talk about. So come on up, George. Okay. We also want to welcome those that are watching on the live stream, either watching live or watching after, when it was convenient for you. So hope you enjoy.
Okay. Hopefully we can get some music going here in the background. See some weird space music. See if this works. Yeah, it works. Okay, now I have to go over here to back where I was. I just want to hit a few things to start with. Basically, welcome to AstroFest, which Drew already told you. 2023, we've been running this a pretty long time. A little history of where it came from is back in the 1980s, a couple of people came up with this idea of Astronomy Day, something to celebrate astronomy. And it never quite fit in what was going on at Kopernik, so we created this AstroFest. And we've moved it, normally Astronomy Day is in the springtime, but we moved to the fall. So that's basically what AstroFest has always been, is our version of Astronomy Day. And the rest of this is just celebrating astronomy. Let's look at some pictures, enjoy yourself. You can walk in or walk out. Anybody has any questions about any of these objects, you can talk to me later, or any of the other astro guys who are here. And this is a collection of, I don't know if it's best or not, but images that I've mostly taken here at Kopernik using Kopernik equipment. Some stuff taken at Cherry Springs, Dark Sky Park in Pennsylvania, where the KAS goes, I don't know, often. And some of it at my camp that I rent in Indian Lake in the central Adirondacks. But that's mostly where this stuff comes from. Again, 90% or more of it is taken here at Kopernik using Kopernik equipment. And if there's anything wrong with the images, it's my fault, it's not the equipment's fault, because I did the processing. And a lot of this stuff is kind of old. I could do a much better job at it now, but we're just here to kind of cool and chill and see how things going. There's me at the telescope way back when, the 20-inch, where a lot of the images were taken. Me at Cherry Springs with my 5-inch refractor and Losmandy mount and one of my cameras doing some imaging. That was in 2018. And me at Stellafane, I don't know how, just some of the other pictures. That's my refractor again, and a 20-inch Dobsonian, which I no longer owned, sold it to somebody else. I have a different 20-inch now. But what we're going to do is just go through these images, and if I can get this to run as a slideshow, I will. If I can't, I will click my way through it. But yes, the Earth does turn. You'll see that Polaris is a little bit off the actual pole, kind of rotates around, but put your camera on a tripod, open it up. This is an old film image. That's how old it goes back to. But get those old nice star colors, and good old comet Hale-Bopp from back in 1997, when we made worldwide TV there. The Science Channel, Discovery Channel here ran a program at Kopernik 1 or 2 nights. And this is an old film image also. Some lunar eclipse stuff from up in Indian Lake. Lunar eclipse through our 20-inch, the 2004. This is, again, old film stuff. And I'm just going to go through deep sky images, most of them taken with our 20-inch here, some were taken with other stuff. And it'll kind of introduce it, and if anybody has any questions later, we will go over it. This is a star-forming region. Oh, our 6-inch refractor that's just been refurbished and reinstalled out in the dome. Great for solar lunar planetary, but can be used for other imaging too. One of our KAS members, Art, doing something, I don't know, trying to break the scope or something. Yes, we do have auroras here. One of the great aurora packages from November 2010. We had a great aurora here. The Broome Community College had its classes going on at the same time. Professor couldn't get any of the students to pay attention. They were all outside looking at the aurora. This is more film stuff. Another KS member, Patrick, working on our new C14 that's out there. Don't have any C14 images yet, but maybe some other people can add them. There's our observatory sitting under, taking drone image under a nice fall day at some point in the past. Back before we painted the domes, they look a lot better now. Again, before we painted the domes. We call this our Sprinxonian. It's a 12.5-inch New Moon Telescope's Dob, but it's modified so that the eyepiece, which is right here, never moves. It's always at the same altitude, so it can be used by people in wheelchairs. And it's a very, very nice telescope for that. This is Ryan Gootson, the guy who designed and built the scope, and Patrick, who was here helping receiving the night that it was brought here. Our 20-inch scope with the new FLI CCD system that's on the back of it. Again, you can see that CCD system. Some of these images were also taken with this small 80mm refractor over on the side. This is a 1980s era telescope, so it's not quite up to what you're going to find available today, but it still does a pretty nice job. I'm talking about the refractor here. The 20 inches, a superb instrument that we're working on. The FLI camera, finger-like instrumentation, these are made in those exotic lands of Rochester, New York, and Binghamton, New York for the filter wheel and the focuser, which is not on there yet. Hard to believe that world-class imaging gear is made right here locally, but it is. Most of this stuff goes into biomedical engineering, but the people who make it are all astronomers, so they're interested in it. The control system for operating the camera and the telescope in the dome. Pot of gold over here, which we found just old eyepieces when we got over there that the bear had been licking. Here's Jeremy and one of our interns looking at bugs in Pennsylvania, or collimating their telescope. I don't know how that got in there, but they probably have a better view than we do, at least tonight. Again, dome's not painted yet, but got to update this to some new pictures. Just some constellation shots from Cherry Springs, just a DSLR and a tripod. You can see M44 open star cluster right there, which is actually a naked eye object from down at Cherry Springs State Park. Again, this stuff could be improved tremendously with new processing, but the Crab Nebula supernova remnant, 1054 AD, was when it first appeared in earthly skies. It's recorded in Asia, in China, Korea, Japan. They recorded this explosion. You could see this thing during the daytime when the star exploded. You could read by it at night. It must have been cloudy for a year in Europe because it was never recorded there. But then in Europe at that time, if you said you saw a new star in the sky, you'd probably be burned at the stake. So everybody kept their mouth shut during that period of time. But fascinating object. Globular star cluster M3. This is taken with my little refractor from Cherry Springs, I believe. And there it is through our 20-inch. May 2019 says the date on it. The argument back and forth as to whether this is the best globular star cluster in the northern sky or M13. Take your pick, they're both pretty spectacular. This is same thing with a different camera, older camera in the 20-inch. M5, another springtime globular. This stuff could all be improved, and hopefully it will be not too long from now. Lagoon Nebula in Sagittarius. This is a star-forming region, glowing gas all lit up by the brightest star in here. Probably Messier only saw the star cluster. Well, maybe he saw the nebula, it's pretty bright. But again, star-forming region. Globular star cluster M10 in Ophiuchus. There's M13 through my little refractor. Another one through the little refractor. And I don't know, do I have it here? Yes, in the, again, through the refractor, this galaxy here, NGC 6207, is fairly bright. It's about 9th magnitude. But this galaxy here, IC 4617, is magnitude 16.5. And here we have the magnificent M13. The interesting thing about this is the tremendous difference in distance between these objects. This may be 15 to 20,000 light years away. This may be 20 or 30 million light years, and this vastly far different. The other thing that was interesting is my own 20-inch Dob at Stellafane for the last 2 years. We've been able to see all three of these objects easily. Well, maybe this 17th magnitude wasn't easy, but you could see it in my 20-inch Dob, all in the same eyepiece field, which was kind of interesting. This is, again, M13 with an older camera. Again, obviously I like M13. M15 is a gem of the current sky. Went out there in Pegasus. Its main problem is it's small but bright. This is a picture from the Adirondacks with my 5-inch refractor. Actually, my notes say this is from my front yard, but went through the 20-inch. Go a long way from a 5-inch to a 20-inch telescope. M16 on the Eagle Nebula. I prefer another old name, the Star Queen Nebula. And you may recognize this as the famous or infamous pillars of creation in here. This is with a narrowband hydrogen alpha filter through our 20-inch telescope. And here this is fake color, but red is H alpha, and I set oxygen 3 filter, which is kind of a bluish green teal kind of color. So I set it to both blue and green, and it gives you something close to what the true color would be. Not exactly. This is the Hubble palette for Hubble Space Telescope assigned the people who do the imaging there. They're primarily interested in scientific study rather than artistic, whatever. So they have these oddball colors that they assign to these various narrowband images. So they put, this is their color scheme for it. M17, this could be a lot better now, but a real old picture through through our 20-inch telescope. M18 is a open star cluster right in here. It's not too spectacular, but it's in the general area of M8 and M20. M20, the Trifid Nebula, through our 20-inch telescope. Very interesting. If you look at this naked eye through anything from like maybe an 8-inch larger, you can actually see this, this dark stuff. And that's not where there's gas missing. That's where there's dark dust and gas, cold dust and gas that's in front of the nebula. And the difference here, this blue stuff up in here is reflection nebula. It's just reflected starlight, where here the gas is actually glowing like neon and a neon sign from the ultraviolet light and more from the new stars that are forming in the star-forming region. This was taken from Cherry Springs with my 5-inch refractor. And again, you can see some of the Milky Way and some of the dark areas in here. And there's that M18 open star cluster down in here. M22, and this is a big, easy to see cluster. It would be very popular, except it's really low. So it tends to be a difficult object to see from the northern hemisphere, but you can see it. It makes nice view. That's through my 5-inch refractor. M23, big open star cluster here, and you notice some dark nebulas over in this port. This is the M24 star cloud, and I'll show you that in a minute. Messier added some things that really are a little bit strange, but this is an easy naked eye object. Some people think it's this small star cluster here, NGC 6603 is actually M24, but it isn't. And there's a couple of dark nebulas. Again, this is not an area where there's no stars. It's an area where there's dark gas and dust, cold dark gas and dust, that's blocking the view to the stars behind it. Okay, this is from Indian Lake, New York, and the Central Adirondacks. I have much better stuff than that now, but you can see the Milky Way. One of the nice things about this, on a calm night, you can actually see some of these objects reflected in the lake. But that's that M24 star cloud right there. So you can see it's big, easy, naked eye thing. This constellation down in here that Corona Australis is a very, I mean, I can just get it as it goes through the notch down the lake. Indian Lake is like 17 miles long, mostly wilderness lake, and I'm looking nearly straight south. You don't see too many pictures of that from New York or the northern environs. It's amazing how deep I can go in that notch. The planetary nebula, now, that's a very bad name. The first guy who started recognizing these things, William Herschel, said, well, this looks just like that planet I discovered a little while ago, Planet George. Well, actually, it's Uranus. He wanted to name it George because he figured King George would give him a lot of money, but nobody else liked that, especially the people in Germany and so on. So they called it Uranus. And he said, well, these nebulas look like look like faded versions. They tend to look greenish, some of the brighter ones in telescopes. And so this name, planetary nebula, kind of stuck. Herschel kind of thought that they might be new stars, planetary systems forming, which is a good guess. He knew it was some sort of gaseous cloud, but it's actually a star that's dying. So it's not a supernova explosion. It's a slow sloughing off of material from an old dying star. And you can see it's kind of heading out here, and it's running into some of the hydrogen, so it's glowing red here. And you got these two ears that kind of point out the side. That sort of stuff being blown out the north and south magnetic poles. This is another image of the same thing taken with our 20-inch telescope. Probably need to go longer on this some night to get a better image of it. Here's a narrowband version through the same telescope where the red is H alpha and the rest of it is oxygen 3 that's been coded as both blue and green, since it's a teal, I guess is the color people call it, bluish green color. So I just kind of mixed both of them to try to get something that was M29, which is one of the least spectacular of the Messier objects. Little open star cluster here. These things are also called galactic star clusters because you can find them mostly along the Milky Way, along the plane of the galaxy. And they tend to be, they're not all, but they tend to be very young objects that have recently formed, relatively recently. And the gas cloud that they formed in is blown away, and what's left is the star cluster, which will, most of them are eventually ripped apart by the gravitational pull of the galaxy. This was, by the way, this picture was taken with my 5-inch refractor. And this is another picture, another version of the same thing, taken from my house of all places. This is just a DSLR camera with a telephoto lens and a tripod on a little tracking mount from Indian Lake, New York. And you can see the Andromeda galaxy. And there's another little galaxy right here, M32, which is a small elliptical galaxy that's in orbit around this thing. And this is M110, which is another disturbed galaxy that's in orbit around M31. This is probably the most distant object you can see with your naked eye. Some people, like I could at one time, can see M33 naked eye, but about 2 million light years away, and it's heading right towards us. So if you come back in about 4 billion years, we have a good show here at Kopernik when it arrives and runs into the Milky Way. I'm selling the tickets later tonight, so if you want to buy the tickets, you can when it comes. So that's the sort of thing of just a little tracking mount with a telephoto lens. And this is Cherry Springs State Park through my 5-inch. And you can, hidden down here, unfortunately, just at the bottom is M32. And that's the 110, the other satellite galaxy. But this is really an object best seen in a good pair of binoculars. The 80-millimeter Brandon on the side of the 20-inch telescope, taken right here at Kopernik with a DSLR. Tupper Lake, New York, October 2017 at the imaging conference up there. I took this mosaic of images with my 5-inch. And here you can see that 110 just barely, but there's M32 in there. Again, it's just a big ball of stars that's in orbit around this galaxy. and I wasn't being too specific here because we were trying to help other people do imaging and so on. There's the color is terrible, but that's the nucleus of the Andromeda Galaxy through our 20-inch with September 2019. It doesn't have a COVID mask on, so I don't know what's going on here. But I imagine that if we wanted to take the entire galaxy with the 20-inch, it would take us the next 20 years to gather all the pieces we would need to put it together. But another telephoto version of it. Okay, there's elliptical galaxy M32 on the edge, and you can see some of the dark dust lanes in M31. And I would bet if you got really close and looked at some of these dimmest stars in here, that they are actually stars in the M31 rather than Milky Way stars. The rest of these stars here are all stuff in the way. They're foreground stars in our own Milky Way, so they're no more than 1,000 light years or so away, rather than the tremendous distance to these galaxies. Another one of the local groups, the M33 triangular. Back when my eyes were good, I could see this naked eye from the Central Adirondacks. I'm going to bet that I don't have it in my notes, but I'm almost certain that was taken with my 5-inch refractor from Cherry Springs. Yeah, Cherry Springs, October 2015. This is a image which could be improved substantially, taken through our 20-inch telescope. Another more modern one. Okay, open star cluster M35 in Gemini, that's this great big thing. And there's a smaller star cluster, more distant, off to the side. I forget its NGC number right now, but a good 8 or 10-inch telescope will show you both. M35 is probably best seen in a pair of binoculars, but it's pretty cool. And that was, again, taken at Cherry Springs State Park in Pennsylvania with my 5-inch refractor. Another open cluster in Auriga, M36, again the 5-inch from Cherry Springs. One of its neighbors, M37. This is M37 taken from my front yard up near the Broome County Airport. M38. Lots of other interesting stuff in the constellation of Auriga, but how much longer have I got to go here, Jerry? How much longer do I have to go? A little bit longer? Yeah, I may have gone a little bit too far here. Okay, and find out when our speaker is M39, which is this collection of stars here in the center, is probably one of the less interesting of open star clusters. But again, looks neat in a small telescope, not so much in a big scope. That was taken with the 80mm Brandon on the side of our 20-inch telescope outside, so you can take a look at the scope that took it later. And the same scope taken with my 5-inch. Now the cluster is a lot bigger, maybe more boring. Yeah. My 5-inch is f7.5, and I have a focal reducer, which I haven't used yet, which will cut it down to f5.5. It's a triplet. Oh, here's a really exciting Messier object, M40. It's just 2 stars. I forget why I took that. I have no idea. Other than I had a goal of taking an image of every one of the Messier objects, and that's taken with our 20-inch telescope. Some views of the Orion Nebula, M42. This port is M43. Every new astro imager heads right to the Orion Nebula, and yet it's one of the most difficult objects to actually image because it's so much brighter in the center than it is in other locations. And I hope to do even better stuff on this. Cherry Springs 2015 with the 5-inch refractor. And again, I certainly hope to do better than that in the near future. Here's with the 20-inch with some narrow band filters. You can see the trapezium, the 4 stars, there's actually more of them. That's providing all of the ultraviolet light that's lighting this whole thing up and making all that gas glow. But there are many, many stars being formed in this thing. In H alpha only. That's again, I think through my refractor with a CCD camera. Through the 20-inch with, again, you can see the trapezium a little bit better. And these are narrow band filters. It's hydrogen alpha is red and oxygen 3 is blue and green added together in there. All that stuff could be better. The beehive cluster in Cancer, again, a springtime object, and you can actually see this naked eye from a place like Cherry Springs or Central Adirondacks, maybe here on a good night. Looks really good in a pair of binoculars. The Pleiades star cluster, this goes way back. I believe this may be filmed through the 80 millimeter, and this is through my 5-inch refractor from Cherry Springs. And this is zeroing in on one of the stars through our 20-inch, and all this stuff is nothing but sort of an instrumental defect in the camera and the telescope that I had to get rid of. All of that nebula behind it, reflection nebula. When I was a kid, that was supposedly what's left of the nebula that the cluster formed from, and now that theory is totally thrown out, and they believe that the Pleiades just kind of randomly got in front of a dust cloud, and you're getting the blue reflection nebula. Elliptical galaxies are not particularly exciting, but if you want to take all the Messier objects, you're going to get a lot of them. Just big balls of many stars. Big ellipticals like this could get up to 1 trillion old stars, no new stars being formed. And there's other galaxies. There's another one here. There's another one down there. There's a galaxy over here. And if you get up close, you can see a bunch more smaller background galaxies in the same image.
George?
Yes. Okay. Let me see if I can get to the. I'll see if I can get here to the very end of this.
George, when you took these, you didn't have to worry about Starlink blurring your images.
No, but there's a way that you can get rid of it. Okay, this is what Kopernik was like when I got here. That you know, they found us all in there, and later we will show the stuff as a slideshow or whatever to catch with the rest of it. All right, I will. I'm getting pulled off the stage here, so I'll shut this down, and we'll proceed with the rest of the program.
Well, thank you very much, George. Again, these images are just outstanding, and we know there's more coming. So great to welcome some other people here. We're going to move on to our next presentation, and give me a second. I'm going to do a little bit of changing around. Okay, and if we do this, and we do this, and we're set. Okay. All right, well, again, welcome. Just to reintroduce myself, my name is Drew Deskur. I'm the director here at Kopernik, and it's great to have you here for AstroFest 2023, our 41st AstroFest. What I'd like to do now is actually introduce one of our board members, Dr. Laura Lamish, and she's going to do a. We're going to tag team this presentation, which will ultimately lead to the big event. So, Dr. Lamish.
Well, good evening, everybody, and welcome. As Drew mentioned, I serve on the board of directors for Kopernik, and up here you can see who we are. And I do want to recognize those board members who are here tonight. We are a hard-working group here to support all of you and to support Drew and the wonderful staff of Kopernik. So let me introduce folks, and maybe you can just stand up and wave. So John Spreitzer is president of the board, and John. Irene, I know, is out back selling raffle tickets. Irene Sidlarsik is our vice president. We have Tom O'Brien, secretary. Yep. Becky Brenner, a newer member. Becky is over here. Hi, Becky. And Art. I believe Art. There's Art. And thank you, Art, for this wonderful event. I think I've got everybody who's here, so yes. All right, well, good evening, everybody. So we're just, my slide shows a little, there's Irene. Hi, Irene. Irene is our vice president. So, you know, as board members, we're here because you're here, because we love this institution, and tonight's a special night for us because we are going to be unearthing the 1973 cornerstone to reveal what's behind there. And so I want to do, in preparation for our anniversary year, we've been doing some historical work around Kopernik. So you're going to get a few slides and a little taste of that. So let's talk about what's happening this coming year. Can I use this? Yeah. Let me just... How about I use the arrow? All right, there you go. All right, so this is very exciting. On June 16th, 1974, almost 50 years ago, Kopernik opened his doors and was dedicated as the Kopernik Observatory, serving the good people of Broome County as a public observatory. So we're getting ready now to celebrate our 50th year, the beginning of our 50th year. So technically, that would be June of 1974, but we're actually setting our celebration for October 5th, 2024. So a year from now, short a day, yesterday was a year from today. We are going to be having a wonderful, wonderful event, an anniversary gala celebration in downtown Binghamton at the Doubletree Hilton. I have hold the date. We are very excited, and we certainly hope that all of our community will be there to help us celebrate this amazing event. So that's coming. Hold the date, and more information will be coming out in the coming months related to this event. So as we were talking as a board, we thought, what a wonderful kickoff to figure out, like, what's behind this cornerstone. So I'm just going to give you a few slides kind of to set the stage. Drew's going to take over and share with you who we are today. So my slides talk about who we were or what we looked like 50 years ago. We looked a lot younger. And what we look like today. So, and by the way, and I know this is going live stream, we are collecting images and anecdotal history about Kopernik's history. So if you have information you want to share with us as we prepare for the anniversary year, which is also members of the board working on going through the archives to create our documentary history, please don't hesitate to share it with Drew, right? So You can find Drew's email and phone number on the website. Or just if you come up on a Friday night and want to bring materials, but we are looking for materials to gather and collect and organize into a documentary history of this amazing institution. So this is one document, and so October 1973, so this was 50 years ago, Edwin Crawford declared October 1973 Mikolaj Kopernik Month. So we are kind of in that ballpark of 50 years with this document. But looking at this, some of the language, whereas the 500th anniversary of the birth of the Polish astronomer Mikolaj Kopernik, celebrated in 1973, reminds us that all the planet Earth comprises a brotherhood in the vastness of space. So this language of what connects us, and as I was looking at George's slides and just thinking about how we are all connected to this, to the sky above us and how it unifies us, and I think that speaks much to our history of Copernic as a real legacy of our community. Whereas the world is justly indebted to Copernic, whose studies provided the foundation for modern science. And as we as a board have talked about the purpose and meaning of Copernic, we keep coming back to this idea of Copernic being an institution of learning and an institution of science. And we'll get, as we evolve, as we develop this history, just a snippet of that is, this is one picture of one of the domes being set. And what we have here started as a vision of one person, Richard DeLuca. He was the curator of the Roberson Museum. It was 1969, and he heard about a deal on an observatory dome. He could get this dome for $500. And he went to the board of Roberson and said, this is a bargain. We have to buy this dome. I don't know what we're going to do with it, but I think we should get this dome. One person got a dome. It sat in the courtyard of Roberson for years. It was kind of a curiosity. Until, about 52 years ago, when the Polish Cultural Society was looking for a way to celebrate the 500th anniversary of the birth of Mikolaj Kopernik. So Richard DeLuca met with them, and he said, I've got this dome. And as they talked, this, that, they came to this vision of building an observatory. And as they say in some of the documents, we didn't just want a statue, we wanted a living legacy. So that dome, it's very symbolic, and I thought this picture is symbolic of that beginning for us, of one person with a vision, then connecting with a community with a passion. 1972, fundraising began. By 1973, sufficient funds were raised for construction to begin. And this was largely coming out of the Polish community, the Polish-American community. But it pulled in a lot of resources, and Roberson being a big part of that. So construction began in 1973, and this is an aerial from when it was completed. I'm looking for actual photos of the construction of Copernic right now. And this is the new Kopernik Observatory. Okay, I love that. New, 50 years ago. And so what you see there eventually became encapsulated by what we're sitting in here. And so this wall right here is the exterior wall you see there, okay? So every time I look at this wall now, and this right here was actually the main entrance at the far left of the photo came out. So this was actually the main entrance right here, and when you walk in here, this was the main vestibule area, okay, the lobby. So the new observatory. The dedication happened June 16th, it was a Sunday, 1974, and Edward and Annette Neslick, so Ed Neslick was the contractor who built this original facility. this one. And he and his wife set the cornerstone. So Drew and I have been going around. This cornerstone, which we will be pulling out, was relocated. We haven't gotten the definitive proof yet, but it was originally on the exterior of the vestibule, probably, we think, right about here. So at one point, when in the 1993 renovation that created this space here, this was moved over here. But we still don't know yet what's in back of it. We really don't. I have some information from a newspaper article. So let me see. Let's see. Yeah, so what's inside? I found this article. So according to this June 8th, 1974 article, it says that coins, brochures about the observatory, tape recordings, and soil from Copernicus's birthplace will be deposited inside. So we have some inkling of what might be in there, but we're not sure. So again, this is just to kind of situate us, this is an aerial. You see the vestibule, again, which would have been right here. And we believe that the original cornerstone was on the front of that vestibule. Okay. And that was removed to have what we have today, which is this facility here. And in this slide as well, you can see how we're kind of built around. There's the existing. This is 1973. This is 1993. So in 1993, the community came together again to raise $2 million to build this room and all of the classrooms and add a third dome. So in 1993, a third dome was added to the facility. So I just, that's my small piece, but I'm going to segue to Drew to talk about Kopernik today. But I want to draw your attention to, who we are as an institution. Last year, the board undertook the rewriting of our strategic plan and the reworking of our vision and mission statement. And I just want us to reflect on this, because as I look at you and as I look at the Kopernik Astronomical Society, I look at AstroFest, I look at our board, Jeremy back here working hard. Hi, Jeremy. Kopernik is amazing. I've been affiliated with Kopernik since 1990. I'm looking around at some of you here who've been here longer than that. And there's something very special about this place. And as we move into our next 50 years, our goal as a board is to make sure that this facility, this campus, thrives and grows and continues for the next generation that will succeed us. So in the coming year, there's going to be a lot of conversation, a lot of planning about what it's going to take to sustain this institution. For the young people in this audience, who eventually may be the ones standing up here or serving on the board. So as a board, we're very committed right now to working hard in the preparation for our anniversary year and our anniversary celebration to work towards sustainability of the institution, which is thriving and which will continue to thrive. So I want to just read to you our vision, and then I'm going to turn it over to Drew, and then we'll get to the really exciting part. Kopernik Observatory and Science Center is an organization committed to the advancement of scientific literacy as the foundation for personal and social decisions that impact us all. Scientific literacy is essential to creating an equitable and sustainable world by inspiring all to participate in the improvement of their community, just as the founders of Kopernik did more than 50 years ago. I mean, what we have here is a gem that significantly improves our lives. Opportunities to advance scientific literacy should be available in and beyond school in ways that challenge and engage. And Drew often says we're more than three scopes on a hill. We are three scopes on a hill, but just looking around the room at each other, we are so much more than that too. So with that, in our vision, a little snippet of our history, more to come. And we're really working on something big for the gala celebration in a year. So if you like this, there'll be more. But for now, I'm going to turn it over to our wonderful executive director, Drew. So Drew, here you go.
All right. Thank you, Laura. All right, let's see if I get this to work. And it does. Well, again, Kopernik Observatory is in fact a public observatory. And arguably, we're really one of the best cited and best resourced observatories in the Northeast. I mean, there are other observatories around that might have maybe slightly larger telescopes, but none of them that offer the public this kind of access. So let's talk about our scopes. We have a 6-inch astrophysics superplanetary refractor. This was just recently refurbished, and this scope we use this scope to primarily look at planets, the moon, and when we put a proper solar filter on there, we can look at the sun. We have a 14-inch Celestron Edge HD reflector telescope that was fairly new to us about 4 or 5 years ago, and we use this primarily to look at deep space objects. And if you were here for George's presentation, this is our main imaging telescope. It's a we call it the Kresge telescope. It's a 20-inch optical guidance systems is the company who made it. Richie Creation reflector, and it has this IDEX. It's now IDEX Health and Science company, but it's FLI instruments, and it's a camera that is permanently attached to this scope. It's the ProLine image, and again, among the kind of images that it's offering. The image on the left is Messier 101 that was actually taken with a different camera, an S-Big camera, back in 2009. And if you look in this area here, see that little bright star right there? That little bright star is actually this little bright star. The much brighter bright star to the right, to the lower right of it, is actually a supernova that was actually captured here on a Friday night. That was in Messier 101 back in May of this year. We have a heliostat. It's a refractor that's actually in the next classroom, and allows us to look at the sun safely, and we can project the sun against the wall, and from here to here is actually about 9 feet across. So this was the eclipse that happened back in 2017. And of course we have scopes that we bring out into the yard for the public to view as well. But beyond our work in the area of astronomy, we are in fact an informal STEM education facility. And so there's a program we call the Kopernik Talent Search, and it has many different iterations. Here's actually one of our students at one of our summer camps on a nature hike examining a salamander. And the salamander, no salamanders were hurt in this process. We offer a program called Kopernik Kids, and this is for kids as young as 3 years old through 6 to begin to start looking at the world through the eyes of a scientist or an engineer. We have a program called Girl Power Science, and this is really trying to aim at women, get more girls interested in STEM careers. So this is aimed at girls between 3rd and 8th grade, and we always cover some topic of some sort, and we always have a female subject matter expert come in and talk about the work that she does in this particular area. And on the picture on the right here was actually an astrophysicist down in NASA's Goddard Space Flight Center talking about how she uses satellites to look at carbon dioxide levels and how that affects global warming. And then because it's a video conference, our girls get to ask her questions. And so our girls asked this particular scientist, how did you get interested into astrophysics? And her answer was great. She says, well, when I was in college, I was an English major, but my boyfriend was a physics major. We'd go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy. She now has her PhD in astrophysics and works at NASA. So you never know where a seed's going to get planted, and that's really what Kopernik is all about, is planting seeds. We do a lot of school outreach on the road. This is actually part of a NASA grant that we did this past spring, talking about having kids understand what it's going to take to build a habitat, say, on Mars. So they learned about 3D printing, and then they created their own little 3D habitat and put their astronauts right outside. We have a portable planetarium that we can take to schools and corporations. People used to ask, do you have a planetarium? And I say, yeah, we just would walk outside and look up. But now we actually have a real planetarium, and this has been a great resource to us. We have a very extensive summer camp that's, this past summer was our 31st year. And this is, again, for students entering 2nd grade through high school. And we'll cover a wide range of topics. One of which is actually, we have a camp called Return to the Edge of Space. And this is where our students will build a payload that flies on a weather balloon that reaches over 100,000 feet. So this is actually an image from one of our weather balloons. You can actually see the curvature of the Earth. That blue area, that's actually our atmosphere. And I'm going to show you now a series of pictures. We have one of our cameras that actually looks up at the balloon. So this is the balloon just before it's about to pop. When the balloon first starts and we let it go, it's about 5 or 6 feet in diameter. When it gets up to over 100,000 feet, it's trying to equilibrate the pressure inside and outside. And at this point, this balloon is about 27 feet across. That gold area, this thing here is a radar reflector, and so that the FAA can also track it. So 40 milliseconds later, you can start to see the balloon envelope start to fail. And then this is my favorite image, because it still has that globe kind of look to it. You can see the sun behind there, and then it continues to go through a rapid deassembly, as we would say. We've offered summer camps in virtual reality and augmented reality, and here's Jeremy showing some of the students some of the projects that they were doing. We also have had an opportunity to have our students talk to an astronaut on the International Space Station. And so if you give me a second here, I think I can get this in. We've actually been able to do this 6 times.
NA1SS, NA1SS, Kilo 2 Zulu, Romeo Oscar, are you ready?
NA1SS is the ham radio call sign of the International Space Station. K2ZRO is the call sign of the ham radio station here.
NA1SS, NA1SS, Kilo 2 Zulu, Romeo Oscar, do you copy?
I'm getting a little nervous. This is the first time I've done this. And all I'm getting is static. It has a happy ending.
NA1SS, NA1SS, Kilo 2 Zulu, Romeo Oscar, do you copy, Colonel Wheelock?
Kilo 2 Zulu, Romeo Oscar, we've got you loud and clear. Welcome aboard the International Space Station, November Alpha 1 Sierra Sierra.
Colonel
This is
Wheelock
Brendan. How well are plants
grew
growing
up in
on
Windsor,
the
New
space
York.
station? Over.
Hi, Brendan.
So what I'm going to do is I'm going to just move forward here a little bit.
The plants actually grow very well, but
Now listen how this kid asks his question and how Doug responds.
The way we bathe actually is kind of like just take a wet washcloth and just kind of wipe your body off. We have rinseless shampoo and rinseless soap that we can use to clean our bodies and stuff. So it's not as good as taking a long hot shower, but it works while you're in
So it's the ham radio station here talking.
This is Matthew Colosi. What is the most significant discovery you've made since arriving on the ISS? Over.
Matthew, are you any relation to the Colosis that lived 2 houses away from me when I was a kid?
Yes, I'm Alan's son.
Great question.
Okay, so his dad is Doug Wheelock's neighbor when they were growing up. I mean, how small a world can you be, even though you're flying at 250 miles away in the ISS? So anyway, those are the kinds of things we are able to do here. When COVID hit, we had to stop doing these Friday night programs, and but eventually we started actually live streaming them, and so we actually have now a YouTube channel that has over 13,000 subscribers, a number of which are watching this evening. So hello and welcome to Kopernik, and so practically any one of our Friday night programs will be live streamed. But what's also great about it is that you can also watch it at your convenience, in the future. Also, we have done a number of live streams of actual astronomical events. So Jeremy, who's right now driving our live stream, we call him our live stream astronomer. And so we've done eclipses, we've done meteor showers. We have another eclipse coming up next week, and we'll be live streaming that as well, hopefully. So again, astronomical events that we offer here, we'll do meteor showers from the Perseids. This is actually Comet Neowise from our parking lot. And this is this lower picture here is the eclipse in 2017. We had about 1,500 people here on that day. And of course, we've got the Kopernik Science Park. We partnered with the Junior League of Binghamton to turn what was basically a swampy area out next to the gazebo into a a really useful item, and this has been, we opened it in 2020. Unfortunately, the ribbon cutting was a Zoom ribbon cutting. It was me and the laptop, and the ribbon behind me, and all these windows of people who'd helped us make this happen. And we all cut the ribbon virtually. But this has been a great tool to bring people up to Kopernik, but also it's a teaching tool for us. We've had schools come up, and we talk about the physics behind what's in the playground. All right, so I think we're getting right where I want to be, and that is the cornerstone. Again, this is one of the original pictures, and we think this little white speck down here, just to the lower right-hand area of those original entrance door. In fact, you can see again this as Laura had mentioned, this building right here we think is this long section in here, and then it actually bumped out. And if you examine closely, you can actually see a line of some kind of material here. So that other bump out actually, started right here and came out here. We think this may have actually been part of that original entrance. And so at this point, what I'm going to do is I'm going to get off of this presentation. I'm going to go back to, give me a second here. We'll go to duplicate these displays, keep the change, and then we are going to go to what's going to make this much easier for you to see. That's this camera here. So I'm going to ask our board president, John Spreitzer, to come up here and help me. I'm hoping this is not an Al Capone's vault event. So I think we can start this. This.
Okay.
And then we can just sort of.
Watch your finger.
Yep.
I think the boards are a little bit too far out. This
Okay. All right. Okay. You're just. Okay.
one up for me.
Yeah. Just drop it.
Oh, you're just gonna lay it on
Yep.
his face. Okay.
And we have a box. And that box has a lock on it. All right. Well, what we're going to do is, well, we'll keep all the dust over here. This took me about 3 hours to chisel away all the mortar over the past couple of days. And I don't see a key. And it's locked. Well, this is definitely one thing we did not anticipate.
Hammer and crack it open? Just, how interesting is that?
Yeah, I don't see anything that otherwise. All right, well, just seeing if there's any kind of all right, so you all have to come to the gala, and then we'll have it open. Well, I am. Yeah. I'll be back. Okay, do you see anything? Nope.
No, I don't see anything yet.
Where's the chest?
Get out of the way. Oh, man.
Oh, no.
There we go. There you go.
All right. Polish soil. That's a great first thing to come out. This is, I think, Kopernik was born in Turin, Poland, and so here's some soil from Poland. All right. Then inside we have a number of bags. We got some coins, somebody's car keys. Yeah, the key to the box is inside. Yes, exactly. I'm going to wash my hands for a moment. Pardon me. All right, and so what we're going to do here is, going forward, we will, our display case that's in the back, we will end up putting the information, these items in that display case, over the next year for people to review. So here's a Legionnaires Committee of Hope presents the 13th Mardi Gras Costume Dance, Fountains Pavilion, February 23rd, 1974. We have a looks like a booklet about Nikolai Kopernik, 1473 to 1973. Also, for what it's worth, can you hand me that picture there, please? For those people, when they come up here and give a tour, I always show them this picture. And it's a picture of this stone and part of the founders. The gentleman in the right is Dr. Ed Klosowski, one of the founding members. Richard Miller was a state legislator. There's Ed Neslick. The gentleman in the blue dark jacket is Commander Jim Lovell of Apollo 13. He was up here. This is 2 years after the Apollo 13 mission. And his picture is inside this. Okay, thank you. Then we've got a program for the dedication day, June 13th, Sunday, June 13th, 1974. Some more information about Kopernik. And Kopernik Observatory, another dedication, must have been a mass at St. Stanisław's Church. Oh, a picture. I wonder if this is... Oh, here it is. Doesn't have... Yes, it does. Okay, actually, it would appear that this is, in fact, the original location of the stone. I'm sorry. And you can actually see right here is the sort of that entrance area. So there's actually the cutout is in fact right there. Well, we'll have it for display in a bit.
Is that that's a Polaroid?
Those are Polaroids, yeah.
What's that?
And here's another picture of people that had been here for the original dedication. All right. Nothing would be more suited than to say, pierogi is something else. And here, his view is one with scope. And here is a picture of Richard DeLuca with, George, would this be the Tinsley? Do you know?
No.
Nope. Or maybe it's, or one of the original scopes that was,
That was a cave Newtonian that I believe
Oh.
they donated to the
okay. And here's a picture of Dr. Ed Kozlowski and Val Kozlowski at the dedication. Ed Neslick, the contractor, and his wife Annette. And another picture of Ed, of course, with a hard hat. Of course, you got to get, if it's construction, you got to have hard hat. All right. So we've got those items. Then so these were all part of this. There's, I guess, some description of that. But wait, there's more. We've got some coins, including some Polish zloty, and some American coins, and a Kopernik pin, and then the list of people who were part of the Kopernik committee back in the 1970s. And then finally, American commemoratives, Kopernik stamps. Back when Copernicus was 1973, there was a stamp dedicated to Copernicus, an American stamp. So
What was the price of the stamp?
you don't want to know. 8 cents. 8 cents. So, oh, there's another dime.
What year is it? Should be 74, 73.
We need somebody with good eyes. So, and there's a stone in here. I don't know. That may have been part of the original stone. There's a lot of shale up here. We found out.
There's a rumor which is told to be untrue. I've been told that about 2 years ago that Richard put a chip off the Stonehenge stones in England, and then he said that he didn't. But
Well, it'll go back in. Yeah, sure, why not? All right, well, this turned out better than I thought it was going to. So anyway, this is really exciting. Believe it or not, we actually have another time capsule. Well, soon after this was built, the Kopernik Observatory was donated to the Robeson Museum and Science Center, and they ran it for about 33, 34 years, during which they expanded it to where we are today. And when they did that expansion, they created another time capsule. And so what we'll do is we are going to open that time capsule, and I actually have a way to get into that one. And we will open that one at the gala on October 5th of next year.
Just had an idea.
All right?
Why don't we save that and in our 50th year fill it up and stick it back in there for another 50 years?
Okay, so right. So meanwhile, you're welcome to come up and take a look at these items. Again, we will find a way to display them in our display case, for this next year. So what we're going to do is then we're going to take about maybe a 5 or 8 minute bio break. There are restrooms. If you go back into the lobby, you go down the long hallway. There were some restrooms there. There's some restrooms behind here. And at 8 o'clock, we have an imaging scientist from the Space Telescope Science Institute down in Baltimore, Maryland, who works with all the James Webb images that are coming in. She's going to be zooming in and talking about the work that she does, and you don't want to miss that. So anyway, thank you again for being part of this.
That's really big, but it's so funny that they would lock it.
Yeah. I'm sure you're going to talk all about this. So I'm going to hand this over to somebody who actually knows what they're talking about, and that's Alyssa Pagan from the Space Telescope Science Institute down in Baltimore, Maryland. And so Alyssa, welcome to Kopernik, and the floor is yours.
Awesome. Thank you so much, Drew. Let me get this going. All right. That look good to everybody? Oh, cool. I get to see people. All right. So I'm not getting any audio feedback, but I'm going to assume everything is good. Okay, great. All right, guys. Well, thank you for having me. I'm very excited to be here. As Drew said, I work for Space Telescope Science Institute, and what I do is take astronomical data from telescopes like Webb, like Hubble, and other observatories, and create color imagery that support news releases that you see on NASA's site or Webb's telescope.org site, or to support other educational resources. But before I get too ahead of myself, I want to touch on what Drew was just talking about, how we get here in the first place, because it helps us appreciate what we're actually seeing in these images, because it took a long time to get here. So, going back to Christmas Day, launch day, December 25th, 2021, we got Webb in a rocket. I was in my PJs. It was like at 7:20 a.m. I'm wondering who was watching at the same time. And of course, it was successful. It was very exciting. I'm going to play just a little bit of the launch just in case you missed it. I'm sure you probably have seen it, but it's just very exciting.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 30 seconds and counting. Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Yay, so very exciting. Everyone was chomping at the bit during this time. And now that it's launched, everything's great, right? Everything's easy. Well, no, that's where like the real trouble begins, because as Drew mentioned, this telescope, in order to fit in the Ariane 5 rocket, had to be folded, and therefore it has to unfold in space as it's traveling 1 million miles from Earth to the Lagrange point, which it will orbit and stay. At the same time, there's a lot of other things that it's doing. So there's over 344 points of failure on Webb at this time for launch and deployment. And basically, if any of these things go wrong, the mission is over. It's failed. It doesn't work. So knowing this now is very disturbing to me. But as we know, it's successful, so we don't have to be too worried. But all of these points of failure include things like the unfolding of this telescope, the solar shield coming down, the sun shield tensioning, and those 5 layers, that mirror unfolding, those 18 hexagonal segments having to be aligned, having to be calibrated, all the instruments having to be calibrated. And then of course we have to cool the instruments because they're in infrared. And so that has to be done very slowly, so you don't invite ice into the detectors, which will cause problems. And then of course it actually has to get to its point. But as we know, it's fully successful. And not only that, it's actually more successful than we had planned, because initially it was supposed to be like a 5 to 10 year mission, and now we're expecting more to 15 to 20 years because of the fuel that we conserved. So that's very exciting. And so this is just like a little sanity check look at Webb's primary mirror, which is important to understand, and because you see indications of this mirror and its geometry in the images for Webb. So we see these very unique star patterns. And so every telescope or every optical system has these. And so in the case of Webb, because of its hexagonal mirrors, each individual one has those 6 sides. So you get 6 spikes because the light diffracts from those 6 sides. So you get those 6 major spikes, and then you get 2 lesser spikes because of the strut that's holding up the secondary mirror. And actually that creates 3, but we don't see them because 2 of them overlap with the major spikes from the hexagonal mirror. So when you're looking at a Webb image and you're wondering why do our stars look like that, that's why. It's because of the way that the mirror is, the geometry of the mirror. And so this is just an evaluation image of the alignment of the 18 hexagonal segments. And as we can see that it was perfectly aligned, it's detailed, and it was just, you know, a very quick image, but we see these background galaxies just coming to life, which is something you'll become accustomed to Webb, and it's something that it's meant to do. And so I will be focusing on the near cam, or what I say is the near infrared instrument, and a little bit of the mid infrared instrument in the observing modes, because I'll be talking about imaging. But I would be remiss not to mention the other near spec, etc., that focus on spectra. So breaking down the light of certain objects into its component colors of light to find things out like composition, which is 70%, 75% of what Webb is supposed to do. So a huge component, but we're focusing on the images today. So why do we study infrared light? Or why do we even need an infrared telescope like Webb? So you're probably familiar with the electromagnetic spectrum of light, and we can see in the visible light, but it's a very, very small fraction of the electromagnetic spectrum. So on the right in this diagram, we have the shorter wavelengths, or the higher energy wavelengths, and then on the left we have the lower energy, longer wavelengths, so like your radio, your radar. And so if we only understood just what we could see, we would have a very limited understanding of our universe. And we also wouldn't be able to utilize a lot of the technology that we use today, like microwaving your food or turning on your TV or placing a phone call, things like that. Specifically now we're looking at the infrared part of the spectrum. And you can think of infrared as heat. And this is kind of like a look into how the predator sees. So he sees sort of these heat signatures. So that's why if you're hiding behind a tree, he can see his prey and then he can attack. Now, the mud will not save you from this attack like it would in the predator, but you can get an idea of what infrared light does. And this is actually something that that actually predators in real life can actually see. Some of them can see infrared light for this very reason. And so a more actual application that we know of is sort of these infrared mapping. So like on your iPhones, to unlock your phone, you have these little dots of infrared that help sort of map your face over time, and it will do that like a couple of times, like several times a day. And that's how it knows how your face is changing, if you get a beard, if you have glasses, and then it can continue to map this with infrared light to continue to unlock your phone. So that's just a modern way of that we use infrared. Now, in terms of space, though, there is a translation of visible light and infrared light, or application in space. So in visible light, we can see on the left, we have this opaque trash bag. We can't see through it. And then on the right, we have the same image, but in infrared, and we can see through the trash bag now because we're seeing the heat coming off of the hand. And that's exactly how we're using infrared space telescopes to study space. So in the case of looking like at a galaxy, on the left, we have the Hubble image. So this is visible light, and you can see sort of the bright young stars, which are blue. And then we have sort of this dust that's more red brown, that's obscuring a lot. And then there's like a very bright core. Now on the right, it goes a little bit beyond that, beyond just seeing through the dust, but actually seeing the dust emanate. So it actually looks like a skeleton of this galaxy, because on the right, this is actually a mid-infrared image. So it's just really nice to see these different components or structures or features and these different forms of light. Another reason why we care about infrared light is something called cosmological redshift. And that just means over time, space is expanding. So these really far away galaxies, their light comes to us stretched or shifted, redshifted. So we can only see those very distant galaxies or first stars if we have an infrared telescope that detects it, because it's shifting from optical to the infrared by the time it gets to us. And so Webb is helping us see further. And then, of course, it's a space telescope because a lot of infrared gets absorbed by our atmosphere. So we need to be above the atmosphere in order to detect it. And also, it's helpful to be in space because we don't have to worry about sort of seeing issues. So that is nice as well. And it's important to note that Webb is not a replacement to Hubble. It's more of a team effort. They're supposed to work in tandem, just like you have different medical equipment to help you understand different parts of your body. You have X-ray machines to see your bones. You have MRIs to see soft tissue, etc. It's to complete the whole story and understanding of our universe. So that is why they were designed. So why do we make color images in the first place? Well, first of all, we want to visualize the data. Numerical information is very, very important if you're doing data analysis, you're doing research, you're making discoveries. But when it comes to just seeing it all at once, getting the full picture, you obviously want to see it as an image. And then you want to see these different structures and filters and these different color mapping to help you understand what's happening. And then you want to illustrate the scientific discoveries and concepts, not just for the scientists, but you want to do it for everyone. You want everyone to be able to understand and appreciate and get involved in sort of these new research or these discoveries. And an illustration can really help make that more accessible. And that ties into engaging the public. We want people to get excited about astronomy, interested about astronomy, maybe, inspire a new generation of engineers, scientists, whatever, anything that involves space, just to get people interested. And so this might not be relevant to you if you don't have any sort of image processing background or you don't do photography, but if you wanted to, just if you wanted to, it's cool to know that you can get all this data from Webb. It's available to the public if you go to mass.stsci.edu. So this is the Barbara Mikulski Archive for Space Telescopes that's hosted by Space Telescope Science Institute. And so all of the data goes there, both the raw and the calibrated data, and then and so the calibrated data is normally good enough to work with. There's a pipeline that helps reduce the data, remove a lot of artifacts. Some still remain, and we'll get into that a little bit when we're creating the images. But for the most part, that calibrated data that you can find in MAST is usable. And if it's not immediately public, it will be public within 6 months to a year, depending on what the scientists are trying to do with that research. And so just in case you were interested and you wanted to go, look at some raw, or I should say calibrated images on MAST, there's just like a helpful way to do this. So if you don't know where to start, maybe you can try going to webbspacatelescope.org, finding an image that excites you, an object that excites you. You don't have to do it this way. But underneath of all these images, it gives you information about that object, things like its coordinates, things like its proposal ID, so that's attributed to the data. And this is actually down here. So if you want to get directly to that data, this is actually the best thing that you can do in order to filter it down. But yes, all this information like catalog name can help you find that if you want to look at the data before it's composed into a color image. And then this is a quick example with the Eagle Nebula. So you need to use the catalog name, which is M16. And because JWST is such a, young mission, we don't have to do a whole lot of refining. We can just put JWST as the mission, and then we get only 13 queries. So that works out. And then we just search, and then we can download specific filters, so specific wavelengths of light, which are shown here. And that's important because that's where you're going to assign specific colors to match those wavelengths, and that will give you your color image. So you'll want to download each filter associated with that image and that instrument. So right now we're looking at the near infrared. So yes, this is a lot, I understand. So just in case you're interested. And then of course, you can download the data. Now this is the calibrated data again. If you're interested, if you like data reduction and you like Python and you want to actually reduce the data yourself, you can do that. You just unclick minimum recommended products and then you can get the raw data. So if you're interested in looking in the raw data, you can do it that way. It's a lot of data. It's very large sizes, especially when you're looking at the near cam. It's like 5 gigabytes of stuff. But when you actually get to the filters you want to download, you just want the FITS image. And that's just the way astronomers collect their data because it's easy to have numerical data and also header information about the telescope observation and things like that. But I2D2, I2D is the image file that you want. So you'd want to click on that and download it right here. Okay. Okay, and so just going back a little bit, this is a final image, the Carina Nebula, that you may be familiar with. But there's a lot it takes to get to this point. The first thing is the telescope has a smaller field of view. Very, very high resolution though. But in order to make a large mosaic, we have to have several pointings across this object and stitch it together. So that's the first thing. So we'll start with sort of one image, and then of course we are collecting data in different wavelengths of light, which we'll also get into how we assign those. But this is grayscale first. So all the images and the different filters come out in grayscale, and they go through a calibration process. So this is actually how the data starts out, the first frame. It's just collecting light over time. And what's kind of cool about infrared detectors versus CCDs or traditional CCDs is that you can get a reading without destroying the electrons. So it's nice. And in that way, it's harder for things to saturate. Well, unless things, of course, are much brighter in infrared, depending on what you're looking at. But it's just a very nice way to do things. So this is stage 0. If you're thinking about calibration pipeline, this is just what we get, artifact detectors and all. It looks like there's some like adhesive holding sort of the detector on, so you get all the striations and you get some noise, and this calibration pipeline is to help that. First, we're just building the signal. So we're building the signal of that one tile. Then we're doing all of these different corrections. You don't have to worry about this too much, again, if you're not interested, but just basic things. If you're an astrophotographer, it's like doing your bias and your dark subtraction, and then also a lot of more convoluted stuff. And then we have to make changes for the geometric distortion, and then apply world coordinate system. And this is where the single image is calibrated against each other. But in the next stage, we're going to calibrate separate exposures together for one image. And then we're also going to stitch together all those separate pointings for each image. So it's a lot. It's a lot that gets done before we even get the calibrated data to process or post-process. So after we've done all this, it's like 8 different squares that we made. We form one image and one filter. Now I kind of went ahead of myself. That was kind of like just so you can see the image, but this is actually how the image looks when you bring it onto sort of our display. And because our eyes are logarithmic, we need to be able to stretch this data so we can actually see it on our screens. But there's a ton of data here, and the dynamic range of these telescopes are so great that that's why we need to perform those transformations in order to appreciate that information and bring out those really subtle details in the dark end. Boop. Okay, so getting to the basics is something called image stretching. So this is another image. This is actually one filter of the Webb Deep Field that you might be familiar with, SMACS 0703, something like that, SMACS. But it's like a galaxy cluster. And this is how it looks like on your screen. You can see here, there's information there. It's just hidden on the dark end. These are the pixel values or the brightness values, and they're all pushed to the left. We want to literally stretch them out. That's where the name comes from. You want to see this more distributed across all these different values, so you can discern much better between those different values. And so this is just a quick look at kind of what this stretch is or what's happening with a littler or simpler image. This is a 2-bit image of a parrot. So there's 4 different values here: black, dark gray, light gray, and white. And so we haven't done anything in the first image. That's just linear. And then we do something called a linear stretch. And this is something we don't want to do with astronomy data for the most part. In general, we don't want to do this, because if we do, we are bringing out sort of the darker end, but we're completely losing the brighter end. It just gets mixed up with the dark gray. And so we don't want to do that. We want to preserve the information. So on the right, we do a nonlinear transformation. So you can see we're bringing up sort of those dark values without losing those bright values. And we do that to our SMACS image. Now, This is an example of the linear stretch, which doesn't work very well because you can see that even though the histogram is very nice on the dark end, we've lost some information on the right end, the bright end. So that's why, again, we want to use this nonlinear stretch where we are compassing all the information, but we're spreading it out so we can actually see the different structures and details in it. And if you're interested in this, again, this is just a free program called FITS Liberator, which allows you to do as it says, take the FITS file and just get the image information, stretch it, and then export it out. So then you can combine all your images together to get your full color image. So you got to do that with all the filters though. So for Carina Nebula, which you saw in the beginning, it's composed of 6 different filters. So this filter's names just refer to microns in this case for Webb. So the F090 refers to a filter that's wideband and it is 0.9 microns. And then so on, 1.87 microns, etc. So this is after we've stretched all of our images together to get the most detail and structure that we possibly can. And then we can move on to something called chromatic ordering, and that's how we assign the data. Color. And so this is just a quick look. For some people, there's a misconception that, these images are color from the get-go. But even like a smartphone works where it's taking images or light in 3 different channels, red, green, and blue, and combining them on the fly. Telescopes like that, but much more complicated, of course, because you have a filter wheel that's spinning, specific wavelengths are let through. And that's how you can assign specific colors to those wavelengths, which have astrophysical meaning in order to get the full color image. So that's how it works there. But we are working in infrared, so that's a little bit more complicated because there's not a one-to-one sort of mapping there, right? You're not like, we know what wavelength we see as blue, and we know what wavelength we see as red. But we can use that relationship, where shorter wavelengths we perceive as bluer and longer wavelengths we perceive as redder in the visible, and apply that to the infrared. So essentially, shorter wavelengths in the infrared get mapped to blue, and etc. Medium wavelengths get mapped to green, and then longer wavelengths get mapped to red. And that's how we keep sort of the relationship the same, and how our eyes works makes sense because the more energetic things should appear more blue, and it tends to work out very well in representing infrared light. So we do that. As I said, we are mapping blue to the shortest wavelength here, which is 0.9 microns, and then we are mapping red to the 4.4 microns. Now it looks like there might be an outlier here, and we're not doing anything funky. This 4.7 micron filter actually is within the 4.4 micron filter because it's very wide. So there's a couple reasons why we do this. One, we assign it yellow because this is a hydrogen emission, and it's very important to understanding what's happening in this image. And we also detect it in the 2.12, which is also hydrogen emission. So it's not really cheating too much. And the reason why it's important is because if we assigned it red, it would just get lost in the red filter, that's 4.4 microns. Or if we prescribed it orange, it wouldn't stand out enough. And that's a really important feature that showcases these embedded hot stars. So that's kind of where the aesthetics and the science work together in order to, convey that message. And then before we combine all those color images or filters together, there is a little bit of cleanup. So even though these images are calibrated, there are some artifacts that remain. So things that are intrinsic to the detector. So, like electronic noise, some banding, and then some things that are introduced by the calibration pipeline, like these dark stars that are just to show that these have been saturated. So that's why they're there. So we have to remove that though, because as we know, stars don't have black holes in them. So after we do that, this is the initial color combination of the Carina Nebula. So already looks pretty cool, but we can take it a step further to color balance it. And this is where things may transition a little more into the aesthetics. There's not one period in this process where you're going from science to art. You're kind of weighing both at the same time, and they tend to reinforce each other. But there are aesthetic principles that we're always considering and applying to these images. So things like clarity, and so tonality, the contrast and the intensity, but also the contrast in the color and the overall composition. And so these are important to use not only for aesthetics, but actually to reinforce what's happening in these different filters. So a thing about composition here is that you're probably familiar with seeing Carina Nebula on the left as this landscape, even though north up convention is the right image. Now, Of course, there's no true up in space, so it doesn't matter. But it is a choice we made, and we made it because, well, first of all, on the right, we'd lose some information to get that into sort of a rectangle crop. We don't want to lose information. It's really precious. And then two, it just feels weighted wrong. It feels hard to parse. And there is an opportunity here to make a connection that actually helps with the understanding of what's happening in this image. So we have it at this landscape format where it's a mountainous region, and then we have this gaseous background. You can think of it as sort of these hot stars that are radiating this dust, just like we have mountain regions in our, own Earth that get eroded by weathering. So it's nice to have those parallels because that's the physics is kind of connected. And so going back to the initial color composite, we can tweak this a little bit, and this is where we more have the eye of photographers. So making sure everything's color balanced so that the darkest regions are neutral, or the background. Now for nebulae, that's not really possible to have a background region you can neutralize, but it's something that we generally think of. And of course, we want the star's cores to be white. So that's how we end up balancing this image. And then the decisions that we make here are to push things so that there's a complementary color, sort of color scheme that already exists. But just really reinforcing it so that we can really differentiate these two different processes at work here, the dense dust and the really hot gas that's in blue. So that's kind of like the thought here. And so here's where I push it too much, and that happens when you're trying to really get those features to pop, but you don't want to do that. Like I call this overcooked. So take it a step back. And of course, I am not working rogue at this point. I'm working very closely with the scientists who took the data. So we can make sure that we are representing this object as well as we can. And so at this point, I bring it down a notch. I emphasize sort of the local color contrast between the dust itself to get more of that 3D nature of that. And then this ends up being sort of the final sort of more cohesive look at the end of it all. And so that is one object. This is actually another very similar object, the Pillars of Creation. That was kind of like a general view. And here I'm going to get a little bit more specific, but not too specific, because I know not everyone wants to make these images, but just in case you're curious, a couple of methods that we use. This is a star forming region as well, and it has the same filters that Carina Nebula had, 6 different filters. So that's why the color scheme looks right, because the color mapping is the same, which makes sense. And so one thing that we have to do besides stretching, of course, is remove star cores, and we have our own algorithms for that to do that. You could also painstakingly make sure that that point is replaced with the brightest point, which you think we'd do in the pipeline, but that actually introduces a whole other issue there. So that's the first thing we want to take care of. Secondly, near cam filters actually are different sizes. If you have the short wavelength channel, that is 2 times the size or 2 times the resolution of the long wavelength channel. And so you actually have to scale one to the other in order to align them together. So they might be aligned in terms of coordinates, but in terms of projecting one to another, you have to align them. So normally we scale the 4.4 or the longer wavelength channel up by 2. And that usually they're well aligned, so you don't have to do anything, but sometimes the calibration pipeline's not perfect, the coordinates are not perfect, and you have to do a little bit tweaking yourself, whether that's in sort of like a astrophotography program, or if you're taking it to photo editing software, any of those will work. But that's because we like to use, get the highest resolution as possible. That's why we scale it up. You can also scale it down because these sizes are really big, and you probably wouldn't notice a huge difference. So something that we get in these images are, again, some artifacts that remain from the pipeline that are not, intrinsic to the object itself. And so something we have is banding correction, and we use a lot of different tools. Here's one package that's very helpful. If you do a lot of astrophotography, I highly recommend. It is very helpful in many things, not just banding correction, but it has a horizontal banding and vertical banding correction that's very helpful, though you have to make sure that your axes are parallel to each other or it will not work, or the banding is parallel to the axes. And so this is just an initial look again of the color composite. You can see it always looks kind of like flat at first before you start making sure you're emphasizing the features that you get from these different filters, which has different, composition. And so that's really part of the job here, is to really emphasize the difference again, and sort of that dense dust, which is the orangey color, and then sort of the red stuff that's sort of embedded inside of this dust, which represents these little young stars that are being born. And then you have like this ionized gas, which is in blue. And so because you can see slowly that we are bringing out those features. And then another thing that's really helpful for this process that we do sometimes, especially with Webb imagery, because there's just so many stars, because you are seeing through dust and gas, and so it's revealing a ton of stars, and it's also very sensitive. So you're going to get a lot, and that can be a little overwhelming to work with. So something that we do is remove the stars sometimes. We put them back, but it's just helpful to work on them separately and also not saturate the stars, which are already bright. You don't want to draw more attention to it. This helps you be able to sort of make adjustments to the details that are hidden in the background that are more faint. And it also helps you correct some of the seams that remain from the mosaicing. So you can see, it's kind of hard to see, but there are some sort of seams where they stitch together the different tiles. So I end up correcting that. So that was very quick, but I ended up fixing that, and then we bring the stars back. And then of course, there's some artifacts that remain after the whole color combination that are easier to remove once you've done that. And we end up, you know, sampling some good pixels around that area and filling it up with those. And so it's not a one size fits all. So that's like, so those are specific processes that we used for star forming regions. But, you know, if it's a deep field, if it's a planet, that might require different things. So here is a star forming region, slightly different process though, because we have 6 filters to work with, but we ended up using 4. And you might think like 6 filters is, you know, that sounds better than 4, but sometimes having more filters is not actually helpful because it's just repeating something you see in another filter and you end up sort of canceling things out or making it muddy, like you're mixing just paint together. So you really have to make sure you're choosing filters that really highlight the different things that you want to see. One specific thing that scientists are really interested in is something called polycyclic aromatic hydrocarbons. PAHs, very fancy word, but it's soot, and it's very important. And so the soot is what you see in this 3.35 micron filter. But there's a little process that we do here in order to really highlight those features, the PAHs. There's a little bit of continuum. So there's light that sort of contaminates this filter. So we can do something called continuum subtraction. And all that means is that we're taking one of the wider filters, either above or below it, and subtracting it. So we get rid of sort of that light that's contaminating it. So we can really just focus on the PAHs, the soot. And that's very helpful because then when we bring that in, it's just going to like pop. And so we're going to remove that for a second, just so you can see sort of the process of how this image came together before we add that up. So you can see it's there's color casting in the beginning. It's kind of greenish. Everything's sort of blending together, not a whole lot of depth. So we're working on sort of the color contrast and separation in general to kind of help, you know, bring out these features and define them. And then bam, we put the PAHs in. So that seems like a little change, but it really helps bring that out. And if we didn't do the continuum subtraction, this whole thing would be kind of like a hazy red, which is not the best way to look at this and understand what's happening here. And also aesthetically, it's also not the best. So there's a lot of things, again, you can do depending on the nature of the data and the object. So you can be creative. And so I've been ignoring the mid-infrared, the MIRI instrument, not because it's not great, it's wonderful. I've just been focusing on NIRCam because it's the high-res instrument on Webb. But of course, you can do MIRI, you can do the same process, apply the same process that I've been talking about to MIRI data. And we do the chromatic ordering. So the shortest wavelengths are the bluer color and etc. And so you can see how it was assigned here. It's of course more colorful. It's very different. It's very exotic compared to NIRCam, and of course very exotic compared to Hubble, because we're getting to the realm of just dust that's emanating, so kind of cooler dust, but we can get the heat of that cooler dust. And then another way that we can process images for deep fields is slightly different. Sometimes we actually stack 2 close filters together to make our blue, green, and red channels. And that can help to really define the color separation, which is something that's really important when it comes to deep fields because of what they mean and what those colors signify. And that is generally, the redder galaxies are the farther away galaxies, the most distant galaxies, and the things that are closest to you are white or blue, like this foreground star right in the front. And that's just very helpful to look at an image and be like, oh, I can tell sort of the distance of the other galaxies just by looking at it. And it's also just very, very cool. And then we have planets, which requires a different processing as well, because this is unprecedented image of Neptune. Yes, I gotta make sure. And you can see this is the best we've ever seen Neptune's rings since Voyager. But there's also a lot happening here. We've seen it with a background of galaxies, which is not normally how we see planetary objects, but because of the nature of Webb and how sensitive it is, we do see them. But the treatment of sort of a dim background versus a very bright, planetary disk and semi-bright rings requires a different processing where you're kind of creating sort of HDR composite manually, where you have stretched the background differently to get the details of the galaxies, very hard stretch, and then very more subtle stretch on the rings, which are slightly more bright, and then the disk, which is really bright. So we combine that all together so we can see everything at once, because we want to appreciate everything and not just see a blown out disk or etc. And then this one's not really different than the rest of them, so I'm going to skip it. But this is just a look at, well, actually, I'll go back to it's just using the same sort of chromatic ordering. What's very cool about this object, of course, it's got a protoplanetary disk. So we're looking at maybe a solar system eventually right here. But again, we're using chromatic ordering. 2 microns is blue, green is 3.35 microns, 4.4 microns is red, and the 4.7 micron in this case is orange. And that sounds like, again, what are we doing with the chromatic ordering? Again, 4.7 is very narrow, so it fits within the 4.4. 4.4 extends way past 4.7. But just like making those choices, because the orange of 4.7 works and sticks out better than the reverse. So the orange on top of a red background, essentially. So just making those little decisions. And this you may or may not have seen. This is the first anniversary image to celebrate Webb. So 1 year since the first images. This was released July 12th of this year, and this is Rho Ophiuchus. And this, again, this is the initial color composite. This is another outreach image, and it's kind of hard to tell, but there's actually a gap here because sometimes you get guide starred errors, especially when you don't have a lot of stars to work with. And so we're missing a bit of a tile here, so we tend to have to fill that in. Not necessarily all the time, but we have these really cool hydrogen jets here that would be such a shame to kind of crop out. So in this case, since this is just kind of useless, not useless, but since it's not a huge part of this image, it'd just be kind of dark and dusty. We can use another telescope that sees an infrared and fill it in. So that's actually what I do right here. Fill that in with Spitzer telescope, but of course Spitzer has a lot less resolution than Webb, so it takes like a little bit of a trick to kind of get that to match there.
Alyssa?
Yes.
Could you comment at some point about the star in the upper left-hand corner and why it looks different than the other ones?
Oh, is that because you mean these guys?
Yeah.
Yes. So this is actually very serendipitous. They're just 2 stars that are very close to each other, not necessarily like close to each other, but in our perspective, they're just very aligned next to each other. So it kind of looks something funky is happening, or like it's a duplication. But yeah, it's just the way there happen to be 2 stars that maybe might be very distant from each other, but they line up to be right next to each other.
Right.
So,
You said there's a fraction, from the mirrors that that they're wider than those other stars. It's sort of interesting to point that out. Thanks.
yeah, no problem. Yes, and give me 1 second. I just need to get my power cord because I'm silly and I forgot to plug it in.
Yeah, we've all been there, that's for sure. Like some of us are there right now.
Last time this happened to me, I was plugged in, but my cat got to it and she unplugged me. And I did not notice it, and it died in the middle of the meeting. And I was like, oh my God. But luckily this time I'm good. But yes, so this was row oaf, and this was sort of, you can see how it goes from like very flat again to bringing out those different features. There's a lot going on, so it was really about focusing on how do we showcase everything without it being too distracting that you can't even focus on something. But so that really helps to kind of bring out that contrast and then really differentiate sort of that blue haze from the red jets of hydrogen and so on. And so this is like a completely color balanced image. So I've been talking a lot about outreach imagery, but in fact, most of what we get is science data that scientists wanted. So they're not going to be making these proposals or making these observations to necessarily fit the make an aesthetic image. Now, of course, they will, because it's good data, but it means that we're going to get things like chip gaps. So they're not going to like dither the telescope to fill in those chip gaps because they don't need that for their purposes. They just want to see specific stars and measure those stars. This is NGC 346. Which is a star forming region and cluster in the small Magellanic Cloud. And so you can see there's also differences in integration time. So you have like really noisy areas next to areas where there's a lot of integration time, so the signal is really good. So yeah, you end up working with sort of like these, and you get used to kind of finding different sort of like tricks to fill this in. So normally, since this is 2 microns filter, so it's the lower length, lower channel. So So that's the lower wavelength channel. So that means that there will be chip gaps, but there won't be chip gaps in sort of the longer wavelength right next to that. So I can fill that in because only in the background, because what I'm going to get, the information won't be very different. So we can do that. And that's how we fill in this particular image. And we use noise reducing techniques in order to get that signal to noise to look more correct. And so this is what we end up getting. So big difference, very fun though. And like just a lot of different techniques that you can use, and you can be very creative. A lot of them part of that package that I showed earlier. Now, this is what it would look like if I combined the full color image together without taking care of those artifacts. You can see where there's a big difference in sort of the intensity, where there's more signal. You can see sort of the blue chip gaps that weren't taken care of in the lowest wavelength filter. And yeah, a lot of gradients, color gradients. We got to correct this. So we have to do that to all the different filters. I don't remember how many filters I used specifically for this one, but we do have to take care of that. So this is our initial color composite. After we have done that, applied our different colors, and then of course we corrected for all those artifacts, but we can do better. This is kind of a cool image already, but we really want to get more of that color separations because there's molecular hydrogen here, and then there's hydrogen gas. And so here we can really see the difference between that molecular hydrogen, which is like yellow, orange, and red. And then we have like the magenta, which is more of that sort of tenuous gas. So that really helps show that separation there. And then one last thing that I will briefly talk about is we've been looking at Webb alone. And all of these techniques that I talked about can apply to Hubble. It can apply to Spitzer. It can apply to a lot of different observatories. It gets a little bit more complicated when you get to higher energy. You have to do a little bit different, but in the post-processing is pretty much the same. Now, so something that we can do and we like to do is called multi-wavelength images, where you take different images, or you take different filters from different instruments and different observatories, so like Hubble and Chandra X-ray telescope, and bring them together so they can see like a full story of this object. And so there's a lot of different ways to do this, but the best way to do this is, again, to kind of maintain chromatic ordering with all these different filters, because if you don't, there can be sort of color confusion. Like if you just made sort of a Hubble image with chromatic ordering, and then you just did a Webb image with chromatic ordering, and you put them together, you don't really know what red is because of, Webb or because of Hubble. So just keeping those things in mind in terms of like communication and clarity. But this is an image that was released recently, and the name of the galaxy escapes me at the moment. But on the left, it's kind of, dark and hazy. There's one Webb filter in here from the near cam, and then there's 2 Hubble. So the near cam is like showing those really faint galaxies behind this galaxy that we wouldn't be able to see as well in Hubble. So it's kind of nice to bring them together so you could get the benefit of like the beautiful optical galaxy, and then you can actually see the features that are behind the galaxy. So there's a lot we can get from multi-wavelength images too, where we're combining data from these different telescopes. But I think that's all I have. So if anyone wants to start questions, I'd be happy to ask. Well, I'd be happy to answer. I can ask too, but.
All right, I guess it does work that way, doesn't it? All right, so we have some questions here in the audience. Just raise your hand. I'm going to bring a microphone over so that, here we go. Here's our first question.
What kind of academic background do you have that led you to do this work?
Yes, so I have a very meandering sort of path, but my first degree was actually at Towson University in art and design. So I really enjoyed art. I've always loved astronomy, but it wasn't until sort of my liberal arts college experience that I took the plunge to take more math and science courses because I could, and I liked them. I'm like, oh, I like this. Always loved astronomy. Decided like after that experience, I was going to get another degree in astronomy at University of Maryland. So I got my bachelor's there, and I didn't know what I was going to do until I took observational astronomy. And then that's where I realized like where the art and science can come together, because these images don't start this way from the telescope. It takes a lot of work to get them. And I'm like, who does that? I want to do that. But yeah, that's my general sort of background. I don't think it takes one specific background. I think across the board, my coworker or my colleague, he is got a background in astrophysics, but he doesn't have an official background in art and design. I think it's just more of a hobby. So if you have the talent or the skill or any sort of intersection, I think of the two would be helpful. In maybe a little bit of computer science too, which I started to do, but I'm like, okay, I think I'm done.
Any other questions? Oh, another one here. Hold on.
Yeah, it looks like you're trying to take infrared images and make them look cool in like false color. How much of your effort is focused on trying to make them look like they would look if we were actually close enough to these things so that they wouldn't be so far redshifted? In other words, they'd still be visible light. And the second question is like, is there some commercial software you use to do this stuff with?
So I'll start with the last question because I think that one's easier to answer. There's no like one size fits all program, but ones we traditionally use is PixInsight, which is a very helpful program, more algorithmically based. And then we have Fitz Liberator 2, which is a nice start just to get, that's free software, just to get the Fitz file into a TIFF format and also being able to stretch it appropriately there. And then we can bring it again into photo editing software, whether that's GIMP or some other way that you like. GIMP is free. I tend to use Photoshop. I don't like to say that very often unless because people have a suspicion of Photoshop as being sort of like an action of, you know, Photoshopping, but it's just using it as a tool to bring those images together. In terms of getting infrared to look like optical, I mean, we're kind of doing that because intrinsically when you are color mapping to the visible, that's what you're doing. You're shifting it to that wavelength. So in essence, we're doing that. There's no sort of manual or equation that knows how to take these specific wavelengths and unshift them. But I think it's important to note that when we're talking about like star forming regions, there's no red shifting that's happening there because they're so close. The only thing where red shifting sort of has an impact would be the deep field images. But yeah, there hasn't been like an algorithm to make that. But I would say that in our process, it kind of naturally makes it like it's sort of shifting it to visible. Now, I think the reason why scientists don't really care to make a complete replica of what it might look like in optical, even if if we can only see it in infrared is because, well, it doesn't really translate that way. Just like, let's say, like the structures don't overlap in that way. Like if you have an X-ray machine, you can't really make it into visible because, you know, you have to interpret what kind of flesh this person might have, which is something that people do. But yeah, it's not, you can't really do anything too, you know, absolute. And then, what was my last point that I forgot? Well, hopefully I answered it, but if I didn't, please let me know.
We do have a question from the chat.
All right. Mike Blake from the chat asks, who are the arbiters in deciding which version of a picture is released?
So it's mainly us, but we are, at the same time, we're part of a committee. We're part of a team that includes the scientists. So we might make the final decision in terms of like the official aesthetic, but it's a combined decision. So when I say we have several iterations, it's more of like that's the process we take to get to the final image. But normally it is a collective decision and it's like an easy one. Because normally people are like, yeah, we can all agree that, yeah, this is the best representation of this data, either aesthetically, scientifically, etc. So yeah, we are part of like a whole news team that come together and make sure that, you know, scientists reviewed it. So yeah.
Well, we do have a couple more questions here. Actually, hold on. Go ahead, just talk.
What was the first image you made of?
The first image that I did of Webb, or the first image that I've done of Hubble? I can give you both. So the first image, when I first started working at Space Telescope's Einstein Institute, was actually a comet, and it was so cool to me because it was a fuzzy blob, so it wasn't like the most exciting aesthetically, but it was so interesting because it was one of the first interstellar comets that we'd ever detected. So the fact that I got to, you know, see that and be able to, you know, stretch it, apply one hue to it, even though it wasn't very, you know, rigorous, was very, very exciting for me, and I'll always remember that. And then for Webb, the first image that I processed was actually Carina Nebula, which was also very exciting because it was beautiful and insane. And when it comes to Webb, it was a bit of a new process, even though the overall process is similar. Some of the artifacts, the way that the color separation works, or for infrared, is slightly different. It's kind of harder, at least we thought it would be harder to kind of bring the color in to these infrared wavelengths. But yeah, Carina Nebula was my first, and also was very exciting.
Another question.
From an artistic and science standpoint, both, what is your favorite type of object image to process?
Ooh, that's good and hard. I think my favorite are planetary nebula. I don't know. I find them so unique. No two planetary nebulae are the same. And I think that fascinates me. I love the structure of them. They're so detailed. Like the Southern Ring Nebula is just so much detail. And of course that looks a little bit similar to the Ring Nebula, but in general, like the way that they eject material is different patterns. I just think it's so cool and unique, and yeah, I enjoy those very much.
All right, we have another question from the chat.
Fred Kelly asks, how long does it take to generate a picture like the ones you showed us tonight?
Yeah, so the ones that I showed, like those big mosaics, those can take quite a bit of time. It might take like a day or two for it to run through the calibration pipeline before it gets to me. And then after that, it might take, I would say, like 2 to 3 days to get that initial sort of composite. But usually we don't, well, I wouldn't say usually. Sometimes we don't end up with that initial composite because we like to use the different filters. And sometimes it takes like a little bit of experimentation to make sure that we're utilizing the filters that best showcase the object. Because again, it's not just about using all the filters available. It's about using the filters that actually tell the story and the science the best. So that can take a little bit of time. But my usual answer is it takes as long as they tell me I have, because we have sort of deadlines, because these images get released with publications, so we need to have them out by that time. But yeah, I would say like 3 to 5 days for a big mosaic, much less if we have like one filter image, like for a comet, that would take a couple of hours because it's just one filter we're working with, one color space to work with. So.
All right, any other questions here? Another one here?
Could you give a brief clarification of what stretching is?
Yes. So stretching is basically, like our eyes see logarithmically, which is great because if we saw linearly, that would mean that we wouldn't be able to see anything in dim light. And so basically that's what's happening is we're making sure that we can actually see the data. So the dynamic range of the telescopes, like they're so sensitive to light that we need to compress it. So that's essentially what we're doing when we're stretching it. We're compressing it, or you can think of it as scaling the brightness values. So for the most part, depending on the object that we are working with, we're basically pinning the darkest point and the white point, keeping those the same, but then just adjusting the midtone. So you can kind of think of it as sort of like a gamma in that sense. So the whole point of it is just taking those like dark values that are close to the background and really just making them brighter without making it unnatural, of course. So usually that's done with like a logarithmic scale that we'd apply. So like a transformation with a logarithmic scale or an arc sine hyperbolic scale. Fancy, but they're just, you know, equations that most of these programs do automatically. So you can apply the stretch automatically and just adjust sort of like your point, your peak bright value. So I hope that clarifies it a bit. It's just essentially transforming those brightness values, scaling them up, just like if you took a graph and you try to change your units to make sure you can actually see like a trend. You're just making sure you can actually see what's happening in that sort of scale of data.
All right. Unless there are any other questions, Alyssa, I think. Well, actually, I do. Actually, I've got a question. I understand there have been a number of micrometeoroid events that have, hit either the. I'm assuming the mirrors, but even potentially the solar shield. Do you see that in any way, and how do you compensate for that in the imaging?
We actually do not see that, and I'm not even sure if the calibration pipeline has to deal with it, not that I know of. So I think even the raw data isn't aware of it because of the way that there's 18 different mirrors, and they're all collecting information and focusing it, and then maybe one just kind of
It's a little bit less, yeah.
Right, it just kind of like cancels that, like you drop it because it's just not a good one. So I haven't seen it. Whether or not it exists in the raw data, that I'm actually not so sure. And I could probably talk to the instrument team to see if that's something that they see, but I don't think so, is what I think. I think that calibration pipeline actually already mitigates that because of the different frames and exposures that you get, but not positive.
Right. Now, I also understand that the amount of course correction fuel that was used to sort of get it out to L2 was less than anticipated, which means then it potentially could extend the ultimate lifespan of Webb. Any thoughts or any information about that you can share?
Yeah, I don't have I've been hearing 20 years. That's been like the number I've been hearing, which is great. I don't know how correct that number is, but it's very helpful because initially it was only supposed to last like 5 years, which is not a lot of time, and a lot of the data or a lot of the research we want to do is actually using Hubble and Webb in tandem. A lot of that research will depend on that. So yeah, the fact that it's extended, I think, is going to be very helpful, and will probably change the programs that people do because they're like, oh, well, then we have all this time to kind of see what we see with Hubble and then utilize Webb in order to, tag team.
Right. Very good. All right. Wait, we do have another question back here in the.
Are there others like you in your department who would be working with other types of imaging, such as the Parker Solar Probe and how you turn that into visual imaging?
We don't. So STSCI is the head of science operations for Hubble and Webb, so we don't get a chance to work on that. I'm sure there is an outreach program for them. I guess it's JPL does the solar probe. I'm not 100% sure, but they probably reduce the data and create that. So like sometimes every now and again there's sort of like a collaboration that happens, but it's very rare. Sometimes we work with X-ray data, which is sort of like a different process in terms of getting through the archive and combining sort of the different photons. But yeah, in general, we only officially get to work on Webb and Hubble images for the most part.
All right. Well, Alyssa, thank you again very much. I appreciate you spending your Friday evening with us and in enlightening us on how these beautiful images, they don't just come out of the scope that way. And it really does take a lot of effort and educated effort to make this happen. So really appreciate your time, but also all your colleagues there at Space Telescope Science Institute for the work you do. Keep wowing us.
Awesome. Thanks so much. Yes, thanks for having me, everyone.
All right, thank you. And if you ever make it up north, please, would love to show you our modest observatory as well. But speaking of which, for those of you, especially who maybe are visiting here for the first time, again, unfortunately, the skies are not allowing us to actually look through the scopes, but we would be happy to give you a tour of our observatory and including our big 20-inch imaging scope. So if let me see, I got 2102. So how about at 10 after? We'll meet out in the lobby. Anybody who wants a tour, and we'll take you through. Otherwise, we'll be back here again tomorrow for a number of workshops and talks. So thank you again. Thanks again, Alyssa.
Thank you.
Good night.